Good evening, ladies and gentlemen. I'm very happy to be with you. Welcome to this webinar on dental adhesion with the funny title of Everything You Wanted Always to Know About Dental Adhesion, but Never Dared to Ask. Before getting into the subject, let me give some credits to important people in the field of adhesion. The first one was Michel Desgrange, who unfortunately passed away. And it is a French colleague from Paris who was very much involved into seminars where he tested the force of adhesion with the participants. He used, in fact, a method which was developed about 15 years ago in Geneva, and he got an enormous amount of data with very different adhesive systems. And the other person I would like to give credit in the field of adhesion is another Michael. It is Michael Bonacore, who in fact invented adhesion for dentistry. And as you can see on this slide, at the end the subject is already quite old. The first publications date from 1955. So it is really a subject which is not really new in dentistry, but which still needs some explications, which still needs some implementation in the clinical field. Now, what is adhesion for in restorative dentistry? Many people always speak about marginal adaptation, about sealing of cavities. Please consider that adhesion completely changed the philosophy in restorative dentistry, because due to adhesion, you have adhesive force, and this adhesive force is more than enough to retain restorations in place. So by using adhesive systems, you do not need conventional macromechanical retention anymore. And for me, this is the biggest advantage of adhesion and adhesive systems. Due to adhesive retention, you may completely change the philosophy of restorative dentistry. Just to give you an example, amalgam cavity preparations are completely over in the field of adhesion. This conventional kind of cavity preparation was necessary to get retention of this non-adhesive amalgam restorative material. Today, by basing restorative techniques on adhesion, this kind of preparation is not necessary anymore, because you will get retention of your restorations due to adhesion. So we may have completely different cavity forms and restorative options when we work based on adhesion. Another issue are crowns. Dental crown is a macromechanically retained restoration. When working with adhesive systems, you do not need crowns anymore. It means that you do not need any crown preparations anymore. They are far too destructive and they are far too complicated. Crowns were replaced completely in the world of adhesion with adhesive overlays and in some places also with adhesive inlays. Just to give you an example on that, I would like to show you these two publications of this nice lady who is coming from Barcelona. She investigated, in fact, the marginal adaptation and the retentive forces of crowns in comparison to endocrowns, which are in fact adhesive overlays. And she did it for two different materials, for composite materials and for ceramic materials. And what you can see on this slide is the definition of the three experimental groups he was using. He used on all these teeth which were considered divital. It was an in vitro investigation on divital teeth. He used long radicular posts, short radicular posts, and endocrowns. And as a restorative materials for these three groups, she used in three groups ceramic and in another three groups composite crowns. And just check on fracture strengths of these in total 6 groups. As you can see here, the short post had a fracture strength of about 470 newtons. If you look at the long posts, we had a fracture strength of about 430 newtons, and the endocrowns had the highest fracture strength, which was 552 newtons. What is also quite interesting, that there was absolutely no difference between the ceramic crowns and the composite crowns. By checking on marginal adaptation, the situation becomes even more interesting. What you can see on this table are the results of the marginal adaptation expressed as a percentage of perfect margins. So the higher the numbers, the better is the result. And we have always two columns, one before loading in our artificial chewing simulator and the other one after loading. Let us focus especially at the column after loading and at the luting interface between the tooth and the luting cement. You can see that the long post, the group with the long post, had a marginal adaptation of 91% of excellent margins. The short post of 85 and the endo of 80. So there was absolutely no significant difference between three groups. Even if the group with the long post and the short post was macromechanically retained, and the endo crown was purely adhesively retained. And by comparing composite crowns and ceramic crowns, this is the difference between the white groups and the gray groups. You can see that after loading, the composite crowns and endo crowns performed better than the ceramic crowns and ceramic endo crowns. So, as a conclusion, just of these two small studies is we do not need macro-retentive elements and macro-retained restorations anymore. Adhesion has completely replaced macro-mechanical retention. And this is something which is already lived today. In many places in dentistry, more and more colleagues go away from macromechanically retained restorations and go more and more into the direction of adhesive restorations. A funny comparison is the comparison of the performance of industrial adhesive systems and dental adhesive systems. Let me give you an example. There is an industrial luting material which is called Scotch welt, and this luting material was applied to glue together a metal surface where at the end they put a truck of 10 tons of weight on this metallic surface. And the diameter of the surface was only 7 centimeters, meaning that the adhesive force, which was at the end in function in this experiment, was 24.5 megapascal. It's quite interesting that this was sufficient to get a score in the Guinness World Record book in 2012. By comparing this adhesive force of an industrial adhesive with the adhesive forces you can have in the dental adhesive world, you realize that dental adhesives are extremely, extremely performant. For example, in this investigation, Scotch Bond Universal had an adhesive force of 35, 32 megapascals. So much, much higher than the world winner in the industrial world. Meaning that dental adhesives are really, or dental adhesives in general, are extremely, extremely performant. Now, let me explain how adhesion works, because a lot of colleagues are really confused when they are working with adhesive systems, because they do not know exactly how the components have to be applied and what the different functions of these components are. So this is the reason why I would really like to explain to you some adhesive principles which are general. I'll not talk about adhesion to enamel or adhesion to dentin. I'll just talk in general terms about the principles of adhesion. Let's start with the situation where you have a substrate surface in front of you, which in most instances is contaminated. So for example, the surface of a cavity is contaminated with a so-called smear layer. In case you would like to put your composite and adhere your composite to the surface of this contaminated, or to this contaminated layer on the surface, you will realize that the adhesive force will be limited by the adhesion of the layer of contamination to the substrate, which in the case of, let's say, the smear layer is around 3 to 5 megapascal, which is not a lot, especially in comparison to the polymerization shrinkage forces of composite materials, which may be higher than 20, 25, even 30 megapascals. So just based on this small example, you will automatically realize that if you want to have higher adhesive forces, you will have to remove this contaminated superficial layer, the so-called smear layer. And to do so, you need a material which is called conditioner. This conditioner is very often quite aggressive, so the conditioner will not only remove the contamination of the surface, but it will also attack the surface of the substrate and will remove out of the surface some easily removable portions. And at the end, you will get a new quality of surface, which in many instances will be quite rough, as you can see on the small drawing, and which is now completely clean. Now you could think that you could apply the composite to this clean surface. The problem of the composite is its extremely high viscosity. So due to this high viscosity, it will not be able to perfectly wet this micromechanically rough surface. So you will need, before applying the composite material, something which will perfectly wet the surface. And the material used for that is called the primer. You can see the function of the primer on the slide, and you can see that the primer is able to completely and perfectly wet this surface, which is extremely rough and which has a lot of irregularities. And now in the next step, you could think that you could apply the composite, but look what happens. The composite is highly viscous, and even if the surface where we want to establish the adhesion is already clean and wetted, there will be no connection or no good connection between the composite and the cleaned and wetted surface, because the composite will not be able to connect correctly with the primer. And this is the reason why we have to apply, after the application of the primer, another substance which will in fact bridge the gap between the cleaned and primed surface and the highly viscous composite. And this substance is called the bonding agent. And what the bonding agent in fact will do, it will connect to the primed surface. It will create a kind of a bridge, flatten the surface, and then connect to the composite material. So this is the whole story about the principles of adhesion. What you need to establish a good adhesion to any substrate, not only to dentin or enamel, but also, for example, to a ceramic surface or a composite surface, are three elements. You need a conditioner, which will clean the surface. You will need a primer, which will wet the surface. And you will need a bonding agent, which will create a bridge between the surface of the substrate and the composite material, which might be a luting composite or a restorative composite. Just to detail this principle on different substrates, let us start in this table, for example, with ceramic materials. What you can see on the table are different substrates, like enamel, dentin, ceramic, and composite, and we take already these three elements which we saw in the previous slides, which are the conditioner, the primer, and the bond. Again, let us start to fill up this table on the example of ceramic materials. The conditioner, the typical conditioner for a ceramic material, is hydrofluoric acid in a quite low concentration, around 5 to 9%. The surface will perfectly clean the surface of the ceramic. It will create a rough, micromechanical retentive surface, and it will prepare the surface for wetting. The wetting will be done by an organic silane. The silane is extremely low viscosity. It will wet perfectly this clean surface, and then we will need some kind of a bridging material which will be able to connect to the composite material. And this bridging material is the bonding, and because a ceramic surface usually is quite hydrophobic, you may use a hydrophobic bonding agent to connect to the hydrophobic restorative or luting composite. Let me give you the next example, just to highlight that we are talking about universal principle by talking about conditioner, primer, and bond. Let's assume that we would like to repair an old composite in the mouse, or that we would like to establish adhesion to a composite overlay or a composite inlay. In that case, we will clean the surface of this composite not chemically by an acid, but mechanically by using sandblasting and preferentially aluminum oxide. After sandblasting of the surface, we will have to wet it, and we may use the same material which is used also for the surface of the ceramic, which is the organic silane. In the next step, very similar to ceramic, we will apply a hydrophobic bonding agent, and we will proceed with the application of the composite material. Very simple, and at the end, it follows exactly the principles of adhesion. Another example is adhesion to enamel. Here again, we first have to condition enamel with a specific agent, with a specific material, which is phosphoric acid, highly concentrated phosphoric acid in the concentration of about 35 to 37 degrees. And then something quite interesting is the fact that enamel which has been conditioned by this kind of acid has a very reactive surface. In this specific case, it is not necessary to apply a primer, which just wets the surface, but this is completely sufficient to proceed with the application of a hydrophobic bond, because the hydrophobic bond will be fluid enough to wet, and it will at the same time create the bridge to the restorative or luting composite. So you can see on this example that it is possible to simplify this adhesive process in specific cases, such is the case, for example, in enamel. Let's come to dentin. Dentin follows the same principles. There is nothing special on dentin. It is only special in its composition, which, in contrast to enamel, is different. And there's one specificity which is important for dentin in comparison to enamel in the work of adhesion or in the field of adhesion. It is the fact that dentin is hydrophilic. Now, let us go through the three elements of adhesion. First, we will have to clean the dental surface. In many instances, a lot of colleagues are using phosphoric acid for that, very similar to enamel. But because dentin is much less mineralized than enamel, the etching time with phosphoric acid must be much, much shorter. Instead of etching, for example, 30, 40, or even 60 seconds, which is the case usually on enamel, dentin cannot be etched for more than maybe 10, 5, 15 seconds, not more than that, because otherwise dentin will get very, very rapidly over-etched with this kind of acid. Then we need a material which will wet this cleaned dental surface. And because dentin is hydrophilic, we will have to use some hydrophilic monomers for wetting, which are then followed by the application of an amphiphilic bonding agent. You may remember that on the surface of ceramic, composite or enamel, we may use a hydrophobic bond, which is well compatible with a hydrophobic composite. In the case of dentin, we have to bridge the difference of hydrophilicity of dentin and the hydrophobicity of composite by applying an amphiphilic bonding agent, which is from one side hydrophilic, from the other side hydrophobic. So this is quite specific really for dentin. The good message is that you may use an amphiphilic bonding agent not only on dentin, but also on enamel, ceramic, and composite. There is not an enormous difference between a hydrophobic bond and an amphiphilic bond on ceramic, composite, and enamel surfaces, but there is quite a big difference between a hydrophobic bond and an amphiphilic bond on dentin surface. For dentin, you need an amphiphilic bonding agent. Now, coming a little bit more into details with dental adhesives. What I showed you on the previous table is the principle and is one example of a dental adhesive system, which is in fact a kind of a conventional adhesive system where you need 3 steps to establish adhesion on dentin by using a conditioner, phosphoric acid, a primer, a hydrophilic monomers, and the bonding, amphiphilic bonding agents. And in the field of dental adhesion, there is the tendency to simplify. Very similar to what you saw already when we talked about adhesion on enamel. So instead of using 3 different materials, just using only 2 or maybe only 1. And this is what I can show you on this table, just to explain you how the simplification in fact happens. You can see on the left-hand side the conventional three-step technology, where we need one material for each step. So we need a conditioner, we need a primer, and we need an amphiphilic bonding agent. In this case, we are talking about a three-step adhesive. Now, when we want to simplify in the field of dental adhesives and cut from 3 to 2, we have two possibilities. Either we take priming and bonding together, and then we have a prime bond, where we have to condition the dental surface before we set specific conditioner. Or the other possibility is, which is much more used today, to put conditioning and priming together, which results in a self-etching primer, in fact, and add a bonding agent. And this is a simplification from 3 steps to 2-step systems. If you want to go further and simplify from 3 to 1, you have to put conditioning, priming, and bonding in one single bottle. Because the conditioner on the surface of dentin is usually an acid, there is a problem of the aggressivity of this acid in conjunction with monomers. When you are using a strong acid, which is part of this one-component system, this strong acid isn't compatible with methacrylate monomers. They will disintegrate during storage, and the adhesive system will not work. So if you want to create a one-component adhesive system where you mix the conditioner, which is an acid, and the primer and the bonding, which are methacrylate monomers, you have to separate, for storage reasons, the acid and the monomer part. In that case, you will end up with 2-bottle, one-component system, where the 2 bottles have to be mixed immediately before application. If you want to create a 1-bottle, one-step adhesive system, in that case, you cannot use a strong acid. You have to use a weak acid together with these monomers. And this is the way where a lot of manufacturers are developing their systems, adhesive systems right now. They are combining a kind of a weak acid or an acidic monomer together with methacrylate monomers, and this results in the development of a so-called one-step, one-component adhesive, where the action of the acid is not extremely strong. This is why very often they are also named as mild or medium pH one-step, one-component adhesives. At the end, very, very simple. Just to show you some examples of the action of these different adhesive systems on enamel and on dentin. Let us start with enamel. What you can see on the left-hand side of this slide is a burr-cut enamel surface, which is covered with a smear layer. The middle portion, the picture in the middle of the slide represents an enamel surface after application of a self-etching adhesive system, just after the application of this self-etching primer. You can see that due to the quite low aggressivity of this self-etching primer, the surface is cleaned, but it is not aggressively attacked by this acid. And on the right-hand side, you can see the action of a very aggressive phosphoric acid on enamel. This phosphoric acid not just removes the superficial contamination of the surface, but it also attacks the substrate, which is enamel, and it exposes enamel prisms. And this is the reason why you can see this typical and nice etching pattern on enamel. This is also very similar on dentin. What you can see on the left-hand side of the slide is burr-prepared dental surface. It resembles a lot to enamel because, again, it is covered with a smear layer. By applying a self-etching primer, you can see that the smear layer is removed, but not completely removed. Especially you may see some remnants in the dental tubules in the middle of this slide. This is the picture which is shown in the middle. And when you apply an aggressive acid, for example, phosphoric acid on dentin, you can see that there the smear layer is completely removed, but also the substrate, which is dentin, is attacked. And this is the reason why these dental tubuli are really wide open, and why also the superficial portion of dentin is also quite aggressively demineralized. Now, when applying strong acids on dentin, there is always the danger of over-etching this dental surface. because there's a very, very narrow window of opportunity in respect to the time where dentin is really optimally etched or when it can be over-etched. And very often it is by applying phosphoric acid a little bit over-etched, meaning that you demineralize dentin and you expose collagen fibers, as is shown on the left-hand side of this slide. The problem of the situation is the fact that then you have to perfectly penetrate this demineralized collagen layer to get a good adhesion. And very, very often, this is very difficult or almost impossible. As you can see in the picture on the right-hand side of the slide, there is a thin brown portion of dentin, which was stained with a brown colorant and which shows exposed collagen which was not perfectly penetrated by the primer and by the bonding of this adhesive system. And this might occur, especially in conjunction with etch and rinse adhesive systems. And this is, of course, a weak zone of adhesion because this collagen can be attacked chemically or even biologically, can degrade, and at the end, the bond on the long term especially may fail. There are some proposals in the literature how this can be avoided. And there is especially the recommendation to use chlorhexidine to impregnate these exposed collagen fibers and thus avoid this chemical or even biological disintegration. But unfortunately, this protection by chlorhexidine works most probably only on the short term, maybe some months, but not on the long term over years. So in my eyes, it is not a very good idea at the end to over-etch dentin and to try to correct that by applying chlorhexidine. It would be much better not to over-etch dentin and to pour it completely with the adhesive system, thus not to use phosphoric acid. What about if you would like to know what is a good adhesive system and what is a less good adhesive system? The question is, what is the reliable data you should have for that? Many people rely in this perspective on bond strength, and they think that if an adhesive system has a higher bond strength, it will behave better in the clinical situation. Unfortunately, there is no clinical correlation between bond strength and performance, clinical performance. So to classify adhesive systems according to bond strength is not a very good idea, meaning that if you are reading about bond strength and at the end you choose your adhesive system based on bond strength, it is not necessarily, you will not get really the relevant information for clinical behavior. To explain you why this correlation between bond strength and at the end clinical behavior is not really relevant, I would like to show you this slide, which represents a study on the bond strength of glass ionomer cements. In fact, glass ionomer cements behave very, very well in class 5 cavities, so there is enough retention of these glass ionomer restorations, even on the long term in the clinical situation. On the other hand, the bond strength of glass ionomers are much, much weaker than bond strengths of adhesive systems. Glass ionomers have bond strengths of about 5, 6, 7 megapascals. Adhesive systems have bond strengths of maybe 15, 20, 25 megapascals. And even then, glass ionomers behave very often better in a class 5 situation than adhesive systems and composite, which shows that bond strength is not the only parameter which is important for clinical behavior. And this is the reason why we do not rely that much on bond strength when we are testing adhesive systems. We rely much more on the evaluation of marginal adaptation by the help of NSEM, surface electron microscopy. Surface electron microscopy allows evaluation with a very high magnification. This is the big advantage, and this is the reason why this kind of microscopy is used when we want to evaluate margins of restorations and the seal of these margins. There is a standard technique which has been used even for decades. It is not necessary to go into details on that, but what is quite interesting that you can connect this technique, especially in vitro, so not on patients, but in vitro, with using extracted teas. And these extracted teas may be revitalized by using diluted horse serum, which tries to mimic the composition of dental fluid, and in this way revitalize these extracted teas and test in vitro in an accelerated way, very, very rapidly, marginal adaptation, quasi like in a clinical situation. And we do this routinely. We have been doing that for decades, and we have a lot of data with many different adhesive systems in respect to marginal adaptation by using this evaluation technique. Here you can see some results of the doctoral thesis of Tiziana Bortolotto. Most probably you cannot read the details. It is not the scope of this slide to show you really the details, but just to show you that we really have a lot of data with this kind of evaluation technology. But what I would like to do is to give you some examples out of these evaluations for different types of adhesive systems in respect to marginal adaptation. Let us start with a classic three-step adhesive system represented, for example, by Optibond FL, because Optibond FL is a very well-known adhesive material, very classic material with three steps. The first step is the phosphoric acid, the second step is a primer, and the third step is the adhesive, or which can also be called the bonding agent. And you can see the composition of these three components on this slide. Now, by checking on the marginal adaptation in enamel and in dentin, enamel on the left and dentin on the right, with our evaluation system, you will get the following results. On enamel, we have marginal adaptation of about 90% of continuous margins before loading in our chewing simulator and of around 70% after loading in our chewing simulator. When looking at dental margins, we end up with about 90% of continuing margins before loading and at about 75% of continuing margins after loading. What is quite interesting, if you compare with our methodology, for example, Optibond FL with Scotch-Bond Multipurpose Plus, another etch and rinse classic adhesive three-step adhesive system, you will see that there are differences, meaning that a class of an adhesive system does not necessarily mean or define the behavior. You may have different results with the same type of adhesive systems, but with two different types of products. But coming back to Optibond FL, at the end, you can consider this type of marginal adaptation as the gold standard in our test, because Optibond FL has a very nice 13-year clinical study, which has been done by the group of Bart van Merbeek, where he proved that this material, even on the long term, behaves very, very well. So it can be really considered the gold standard. Now, what is interesting is to compare this gold standard, three-step etch and rinse gold standard, with some simplified systems. And as I already told you, we have an enormous amount of data on many, many different adhesive systems. But just to give you an example, what you can see here is the marginal adaptation of SE bond from Curaray in enamel and in dentin, always on the left of these two graphs. And you can see that we have a marginal adaptation in respect to percentage of continuous margins of about 90% before loading and maybe about 75% after loading, which corresponds pretty well to Optibond FL. And on dentin, this already simplified system, before loading is at about 95% of its continuous margins, and after loading also at about 95% of continuous margins. So at least as good as the gold standard. And you can see some other adhesive systems, self-etch adhesive systems on this slide, and they behave pretty well and very, very similar to SE bond. So it seems that there's no real difference between the classic gold standard three-step adhesive systems and these already simplified self-etch adhesive systems. And this was also very, very recently confirmed by a study from the same group, again, the group of Bart van Merbeek, where he tested a self-etch system after 12 years. And he found out that the results are really comparable to the results after this period of time for Optibond FL. So even clinically, no difference, which at the end confirms our results from our in vitro test. Just a small detail on self-etch systems. You may remember that I told you that self-etching primers cannot use strong acids because the monomers, by using strong acids, would disintegrate during storage. So most of these self-etching adhesive systems are using relatively weak acids in the self-etching primer, which might be more or less sufficient on cut dentin, but which is not necessarily sufficient on uncut dentin, because the on cut enamel. I'm not talking about dentin, but enamel, but it is not necessarily sufficient on uncut enamel, because uncut enamel is covered by a layer of aprismatic and usually highly fluoridated enamel, and it is very, very difficult to etch this enamel quality with a weak acid. This is why, by using self-etching adhesive systems, it is very often recommended to etch before the application of the self-etching primer enamel, not dentin, but just enamel with phosphoric acid to get enough aggressivity on this specific and very, very special quality of enamel. Now coming to one-component adhesive systems. As I told you, there are two types of these one-component adhesive systems. One type may use quite aggressive acid. In that case, you have a two-bottle system, or you may use quite weak acid. In that case, you have a real one-bottle, one-step adhesive system. When looking back in history to the development of these one-component adhesive systems, the first versions of these one-component adhesive systems used quite aggressive acid. So it was necessary to provide them in two components. And one of these first one-component systems was prompt LPOP, which used quite strong acid. And this was the reason why it had to be provided to the dentist in two different chambers, which were squeezed before application together and produced one single liquid, which was then applied to the tooth. So the mixture was done immediately before application. And look at the result of such a system. You can see that in our test, the marginal adaptation on enamel was very, very good, as you can see on the left-hand graph. But the marginal adaptation on dentin was quite weak. And the reason is that most probably, due to the aggressivity of this acid which was included into the material, this acid was very efficient on enamel, but it just over-etched dentin. And that was most probably the major reason why dental marginal adaptation was that weak. And this was something which happened maybe 6, 7, 8 years ago. And in the last 8 years, many manufacturers focused on the optimization of these one-component adhesive systems and to find a balance between adhesion on enamel and adhesion on dentin. So to improve both types of adhesion with a one-component single material adhesive system. And here you can see some examples what the situation is right now with one-component adhesive systems. On the left-hand side, you can see marginal adaptation on enamel. On the right-hand side, you can see marginal adaptation on dentin. Just to pick out some examples. If I focus on the first version of iBond, it is not the actual version, it is the first version which came out some years ago. You can see that iBond is very performant on dentin, but it is quite weak on enamel. The most obvious reason is that apparently the acid which was used in this product was very, very weak, so it was not aggressive enough to condition properly enamel, but because it was not very, very aggressive, it was possible to establish a very good dental adhesion. The contrary, just to give you an example, based on this graph, is Xenos 3. So it is also the old version of Xenos 3. It's not the actual version. Here it is the contrary. Apparently this material used quite aggressive acid for conditioning, which at the end led to quite good marginal adaptation on enamel, but it apparently over-etched dentin. This is why dental adhesion was quite weak, or the marginal adaptation on dentin was not optimal. But the latest developments at the end are able to create a kind of a compromise between enamel adhesion and dental adhesion. One of the first one-component adhesive systems which was optimized in this direction was G-bond. And if you look at G-bond, you can see that the marginal adaptation of G-bond in enamel is almost the same like with the gold standard OptiBond FL. And on dentin, it is really outstanding. And the latest developments go into the direction of universal adhesive systems. One of the first adhesive systems in this field was Scotch-Bond Universal. You can see that Scotch-Bond Universal is really very, very good on the enamel side and also on the dental side. And again, if comparing with classic three-step adhesive systems, it is at least as good as OptiBond FL, at least in this in vitro evaluation before and after loading under simulation of dental fluid. So for us, at the end, because we believe to our research, we think that these latest generations of one-component adhesive systems and also these universal adhesive systems might be as performant as classic gold standard three-step systems. So we go more and more into the direction of application of these one-component universal adhesive systems also in the clinics. At the end, the only difference for us between a three-component gold standard adhesive system and this new one-component universal adhesive system is the fact that we do not have, let's say, 13 years clinical data with the universal one-component adhesive system. But the in vitro data show that the potential of this kind of development is really excellent. And what is quite nice with these universal one-component adhesive systems is the fact that they are universal. So you may use them not only on enamel and dentin, but you can use them, for example, also on composite and ceramic surfaces. And to give you an example for that, let me show you a case we published some years ago on the repair of an old composite overlay. On the left-hand side, you can see the initial clinical situation, and on the right-hand side, you can see what we did to correct the aesthetically unpleasant situation. We only removed the buccal and the proximal part of this restoration to a depth of about 1 to 1.5 millimeters to create space for new veneering with direct composite resin. And the funny part of this clinical case is the procedure how to establish adhesion. Because here we are in front of a situation where we have to establish adhesion on enamel, on dentin in the cervical part, and on this aged composite material. So it is really a case for a universal adhesive system. Let me go first through the procedure when we would apply a classic adhesive system, not a universal one, but a classic multi-component system. In that case, we would do the following. We would first sandblast the composite surface. This is the conditioning step for this aged composite. Then we would etch enamel with phosphoric acid. This is the conditioning procedure for enamel. Then we would apply a self-etching primer to condition and to prime dentin. We wouldn't apply any silane on composite because silane would also touch dentin, and silane is not a good primer for dentin. So we would replace silane as a primer on the sandblasted composite surface by the self-etching primer of the dental adhesive, and then we would proceed to the application of the bonding agent of this adhesive system. So it is not extremely complicated, but it is true, it is quite time-consuming, and you have to respect the chronology of the different steps. Now, by using a universal one-component adhesive system, the situation becomes much simpler. In that case, the procedure is as follows. First, we will sandblast composite with aluminum oxide. This is the conditioning step for composite. Then we will apply phosphoric acid on enamel to get the best conditioning procedure on enamel. And finally, all what you have to do is the application of this universal adhesive system, which is self-etching on dentin and which will give you all the functionality you need to establish adhesion on dentin, enamel, and composite. So even if the situation from the clinical point of view is quite complex, it's very simple, easy, and reliable to establish adhesion on these 3 different substrates. And this is what you can see also in these clinical slides. The first step on the left-hand side is sandblasting of the composite surface, then phosphoric acid etching of enamel, then the application of this universal one-component adhesive system. We remove the excess of the material. We polymerize well. We pre-polymerize this one-component universal adhesive system by light. And then we proceed to the stratification with a direct composite resin material. And all what was done here was a little bit more complex aesthetic stratification with direct composite in comparison to the initial situation, as you can see in the schematic drawing on the left-hand side. This is the comparison of the situation before and after this aesthetic modification. What is very, very nice on this procedure is the fact that you do not have to remove in total completely the old restoration. So it is much less invasive in comparison to the complete removal. It is also much more simpler, and it is less expensive to the patient, because basically the only problem what the patient has was aesthetic. It was not function. The function was okay. It was just the aesthetic appearance. And this can be very well corrected by this very, very simple measure. And this is the situation from the buccal view. Now, what can you do wrong with adhesive systems? Let me spend the last 15 minutes on this subject before entering into the question session. There are a lot of points you can really do wrong. And I cannot go through everything, because 45 minutes is not enough for that. But just to give you maybe some hints where I think you should really take care. One point is diagnostics. Let's assume that you restore a tooth with an adhesive system and, for example, a direct or indirect composite, and you pre-polymerize the layer of your adhesive system by light before the application of the composite, which should be done always when you would like to have good dental adhesion. You have to pre-polymerize the bonding or one component adhesive, or just the bonding layer, before the application of the first composite layer. In that case, if you do not take care and you do not thin this adhesive enough, you will get a thick bonding layer, which is not very advantageous from the mechanical point of view, but especially if you then would like to check on this restoration by radiographs, you will have a radiotranslucent layer beneath your restoration. If it is yourself who plays the restoration, most probably you will remember that you applied a thick bonding layer beneath this restoration. If the patient will go to another dentist, the other dentist cannot know and cannot judge on what is beneath the restoration, because he will see just a radiolucent zone. So most probably he will have to intervene veneer and change the restoration, which is very, very invasive and at the end not necessary. So be careful not to apply thick bonding layers, with the exception if you are using a radio-opaque bonding agent. Then you may also apply a little bit thicker layers, because you will not see it in the radiograph. So this is a very, very important clinical point. What about pitfalls with adhesion? I don't know whether you are aware of the fact that disinfecting products which are used for the disinfection of units may have a negative impact on adhesion. So when you use a kind of a disinfecting materials for your unit, for your dental unit, and maybe there are still some remnants of this disinfectant in the water you are using to spray and to clean the cavity, you may have some troubles, especially with dental adhesion, because it might not be compatible. So you should check on that with your provider of your disinfecting solution, whether this disinfecting solution is compatible with dental adhesion. Another problem might be subgingival management. A lot of people are using chemical agents to stop bleeding when they have subgingival located margins, especially in the field of crown preparations. Again, I already told you that from our point of view, crowns preparations are not necessary when working by adhesion, but I am aware of the fact that there are a lot of colleagues out there who are still preparing crowns and then working with some kind of adhesive cements. Please consider that chemical agents to manage bleeding might have a negative interaction with dental adhesion. So when you are working with some kind of these products to stop bleeding of your gingiva, or the gingiva of the patient, be careful and check whether this product is really compatible with dental adhesion. Otherwise, the crowns may come out. And I tried to put maybe the most important points in respect to adhesion together, and at the end I arrived at the kind of 10 commandments in the field of adhesive dentistry. And here you can see them, and I will go very, very shortly through them, just to remind you that if there are some troubles with adhesive materials, if you have maybe some debondings, or if you have some failures, it is not necessarily the problem of the adhesive system. It might be a problem maybe also of the clinical technique or of some other materials you are using together with the adhesive materials. So let us go very, very briefly through these 10 commandments. Point number 1, remove biofilm mechanically. This is a very important point, especially in the field of fissure sealings, for example, because do not forget that when you try to seal fissures of a tooth, usually there is a biofilm, there's plaque on top of the surface. You cannot remove biofilm by chemical means, for example, by phosphoric acid etching. You have to remove biofilm mechanically. So the best procedure, especially in the field of fissure sealings, is to sandblast very briefly and carefully the fissure. By sandblasting, you will remove the biofilm. At the same time, you will also remove the hypermineralized superficial enamel layer we told already about, and then you will expose really nicely structured enamel, which can be very, very nicely etched by phosphoric acid. So the mechanical removal of biofilm is a very, very important condition to get good adhesion. The second point is remove highly fluoridated superficial enamel mechanically. We come back to what I told you already in respect to the biofilm. At the end, it's the same thing. Remove the superficial enamel layer, which is aprismatic and highly fluoridated, because otherwise you will not be able to etch it in an optimal way. The third point is do not use caries detector dyes, because point number 1, they are not really selective for caries. They penetrate everything which can be penetrated, so which is porous, and not only caries, so they are not really selective. And second, they may have a negative interaction with dental adhesives, so they may reduce dental adhesion. This is why, at least in our clinic, they are strictly forbidden. Do not use hemostatics. That was the point I showed you in the previous study, where some hemostatics may have some negative effect on dental adhesion, so you should carefully check on that when you are using them. Adhesive systems disinfect the surface, so do not use any specific disinfectants such as sodium hypochlorite or H2O2, because you do not need them. They may have a negative impact on adhesion, as you can see in point 6, and you do not need them because anyway, by applying an adhesive system, you will work with an acid, either a strong acid or a weak acid. And this acid already disinfects the surface of your cavity. So you do not need any additional disinfection. And the disinfection, number 6 and point number 7, like H2O2 or sodium hypochlorite, may have a negative effect on adhesion. We already touched the point number 8 about chlorhexidine, so I will not go back to that. Number 9 is very important. You do not need any calcium hydroxide in deep cavities. The most important in deep cavities is a good seal. And a good seal can be obtained by using a good adhesive system. So don't use calcium hydroxide in deep cavities. Rely on a good adhesion. If you use calcium hydroxide and you do not believe me, in that case, cover calcium hydroxide with a small amount of a flowable composite or of a bonding agent before applying, for example, the self-etching primer or phosphoric acid. Because otherwise, the action of the acid will be neutralized by the extremely high pH of the calcium hydroxide. Number 10, Swirl self-etching adhesives to avoid buffering in contact with the tooth is also quite important, because by using self-etching adhesives, you know that the self-etching primer is not very aggressive. The acid of this primer has a quite low aggressivity. It is thus buffered in contact with the dental surface. To avoid this buffering, you have to swirl the material. You have to move it. And to get always fresh material in contact with the tooth, dentin, and enamel. So do not rub it in, but just move it to get always, all the time of the action, fresh material in contact with the tooth. And 10 amendments were enough for the Bible. In the field of dental adhesion, we have to add another 8. You can see point number 11. Even by using self-etching adhesive systems, they might be not that bad on enamel, but if you want to be sure that you will get the best adhesion on enamel with self-etching adhesive systems, etch enamel with phosphoric acid before the application of the self-etching adhesive or of the self-etching primer. Number 12, this is also a very important point, give enough time to the adhesive for etching and penetration. This needs time because it's a chemical reaction, it's a physical action also in respect to the penetration, and this needs time. So it is not just about application and going to the next step. Give enough time for penetration, for etching, especially to the self-etching primers or self-etching one-component adhesive systems to get the best result. Number 13, air drying is product dependent. Usually, modern one-component adhesives are made in a way that you can really dry them quite intensively with compressed air. They will not disappear from the surface. In the older days, the first versions of one-component adhesives had the consistency of primers, and in some of these products, when you thinned them a lot, they just disappeared from the surface. So there it was quite dangerous to air dry them really in an intensive way. But modern one-component adhesives and two-component, three-component adhesives, you may air dry the bonding agents really in a very, very intensive way because they have enough layer forming capabilities to stay on the surface and to establish the connection with the composite material. Number 14, if possible, give dentin adhesive time for maturation. Don't forget the dental adhesion needs time. You will not get the full adhesion after you stop polymerization. The adhesion still matures and continues to get better, better, and better. So it's quite a good idea to wait a certain amount of time after the light curing of the adhesive system on dentin. Enamel is not necessary, but on dentin, before applying the first layer of composite. Number 16, no pre-polymerization of adhesive on enamel is necessary. There you can immediately proceed to the application of the first composite layer. On dentin, on the other hand, it is really a good idea to pre-polymerize the adhesive system and to wait a little bit before applying the first composite layer. Number 17, one-component adhesives may stick to metallic matrices. In that case, if you are working with such an adhesive system, use transparent matrices, or today there are more and more manufacturers providing you with coated metallic matrices to avoid the sticking effect. Number 17, try to separate dentin and enamel adhesion if possible. Then we go into the subject of selective bonding on dental sealing. More and more people are today, especially in posterior cavities, first sealing cavities with a one-component or self-etching adhesive system, and then refinish enamel, then etch enamel with phosphoric acid, and establish adhesion on enamel. In that way, it is possible to separate completely dental adhesion from the enamel adhesion. And number 18, finally, be careful with chemicals for biofilm control in water lines. This is the point I showed you already on the previous slides, where there might be a negative effect of these disinfectants of dental units on dental adhesion. So, ladies and gentlemen, let us now move to the question session. This session is limited to 15 minutes, and you may ask your questions by chat, and I'll immediately answer them live. We suppose that there will be more questions than time which we have for answering these questions. So tomorrow you will receive a link for this webinar where you can review the whole webinar, and some days later you will also find answers to all questions which were submitted through the chat.
Welcome to Battle of the Bonds, the ultimate hands-on test of dental adhesive bond strength. Since you rely on dental adhesives as an important part of your clinical work every day, you naturally want to know how your adhesive compares to others out there. To answer that question, dentists from the United States, Europe, and Brazil agreed to test their current adhesives in the Battle of the Bonds. In 33 hands-on events, 658 dentists collectively put the pressure on their adhesives to compete against the universal contender, Scotch Bond Universal Adhesive. Altogether, 13 leading dental adhesives were put to the test. Get ready to see which of the top-rated contenders fell short, which ones went the distance, and which one was consistently at the top of the rankings. But first, here's a brief look at the test that was used. Dentists were given 2 lab-prepared test specimens of bovine teeth embedded in an acrylic cylinder and ground flat to expose the dentin, one for testing their current adhesive, and one to test Scotch Bond Universal Adhesive. To create the test samples, dentists first applied the adhesives to the exposed dentin surface, following the manufacturer's instructions for use. With Scotch Bond Universal Adhesive, the dentin surface may or may not have been etched with phosphoric acid, depending on the dentist's preference. Scotch Bond Universal Adhesive was then applied with a brush using a scrubbing motion for 20 seconds to assure uniform distribution across the surface and penetration down into the dentin. It was gently air-dried for 5 seconds to evaporate the solvents and produce a uniform film. Then it was light-cured for 10 seconds. Next, a mold was centrally placed on the cured adhesive and fixed into place with a clamp. A hole in the mold was filled and packed down to create good contact with the adhesive and tooth surface. Any excess material was removed. The composite was then light-cured. When the clamp and the mold were removed, the dentist had a test sample, a cured composite cylinder that was bonded directly onto the surface of the dentin. Each sample was placed in a clamp and loaded into the portable shear bond strength testing unit. The wheel was slowly turned, bringing the shearing mechanism into contact with the composite. Once the Start Test button was pressed, the shearing force against the composite was gradually increased until the composite debonded. The force required to break or debond the samples was recorded in newtons on the electronic gauge. In this example, 83.7 Newton was the force needed to debond the composite using Scotch Bond Universal Adhesive. The final step was to convert the Newton measurement into megapascals, or MPa, which is the measurement of shear bond strength. To do that, the force, or newtons, was divided by the surface area of the composite cylinder, or mm squared. The resulting number equals the value in megapascals, or MPa. In the Battle of the Bonds, 658 dentists put their adhesive up against Scotch Bond Universal Adhesive, round after round. And when the final bell was rung, Scotch Bond Universal Adhesive was proven to be as strong or stronger than the other 12 leading dental adhesives tested. Whether it was used in the self-etch mode or the etched mode to dentin, it's the truly versatile adhesive that can be used with any technique, used for virtually any indication and on any surface, allowing dentists to simplify the dental bonding procedure without compromise. For more information on Scotch Bond Universal Adhesive, visit 3msb.com.
That results in reduced bond strength and patient sensitivity. Scotch Bond Universal Adhesive is different. Its unique formula uses optimized ratios of 3MSB's Vitrabond copolymer, HEMA, and water to rehydrate the collagen network and form a distinct hybrid layer, whether dentin is kept moist or is dry. The hybrid layer provides consistent bonding and virtually no post-op sensitivity in both self-etch and total etch applications. Get strength and versatility from one bottle with one application procedure that only takes about 35 seconds. Simplify your bonding procedures with one adhesive for any technique. One adhesive for both direct and indirect applications. One adhesive for all surfaces. Scotch Bond Universal Adhesive from 3MSB, the trusted name in dental adhesives for over 30 years.
Welcome to Battle of the Bonds, the ultimate hands-on test of dental adhesive bond strength. Since you rely on dental adhesives as an important part of your clinical work every day, you naturally want to know how your adhesive compares to others out there. To answer that question, dentists from the United States, Europe, and Brazil agreed to test their current adhesives in the Battle of the Bonds. In 33 hands-on events, 658 dentists collectively put the pressure on their adhesives to compete against the universal contender, Scotch Bond Universal Adhesive. Altogether, 13 leading dental adhesives were put to the test. Get ready to see which of the top-rated contenders fell short, which ones went the distance, and which one was consistently at the top of the rankings. But first, here's a brief look at the test that was used. Dentists were given 2 lab-prepared test specimens of bovine teeth embedded in an acrylic cylinder and ground flat to expose the dentin, one for testing their current adhesive, and one to test Scotch Bond Universal Adhesive. To create the test samples, dentists first applied the adhesives to the exposed dentin surface, following the manufacturer's instructions for use. With Scotch Bond Universal Adhesive, the dentin surface may or may not have been etched with phosphoric acid, depending on the dentist's preference. Scotch Bond Universal Adhesive was then applied with a brush using a scrubbing motion for 20 seconds to assure uniform distribution across the surface and penetration down into the dentin. It was gently air-dried for 5 seconds to evaporate the solvents and produce a uniform film. Then it was light-cured for 10 seconds. Next, a mold was centrally placed on the cured adhesive and fixed into place with a clamp. A hole in the mold was filled and packed down to create good contact with the adhesive and tooth surface. Any excess material was removed. The composite was then light cured. When the clamp and the mold were removed, the dentist had a test sample, a cured composite cylinder that was bonded directly onto the surface of the dentin. Each sample was placed in a clamp and loaded into the portable shear bond strength testing unit. The wheel was slowly turned, bringing the shearing mechanism into contact with the composite. Once the Start Test button was pressed, the shearing force against the composite was gradually increased until the composite debonded. The force required to break or debond the samples was recorded in newtons on the electronic gauge. In this example, 83.7 Newton was the force needed to debond the composite using Scotch Bond Universal Adhesive. The final step was to convert the Newton measurement into megapascals, or MPa, which is the measurement of shear bond strength. To do that, the force, or newtons, was divided by the surface area of the composite cylinder, or mm squared. The resulting number equals the value in megapascals, or MPa. In the Battle of the Bonds, 658 dentists put their adhesive up against Scotch Bond Universal Adhesive, round after round. And when the final bell was rung, Scotch Bond Universal Adhesive was proven to be as strong or stronger than the other 12 leading dental adhesives tested. Whether it was used in the self-etch mode or the etched mode to dentin, it's the truly versatile adhesive that can be used with any technique, used for virtually any indication and on any surface, allowing dentists to simplify the dental bonding procedure without compromise. For more information on Scotch Bond Universal Adhesive, visit 3msb.com.